Hey, we're Kitrina and Ruby. This is our presentation on basic structural mechanics of the lower steel bridge connecting buildings G and E on level 3 at Victoria University. We look at the bridge design, load analysis, and internal forces. For all phases, the phase before it is essential to the calculations and equations for the next. Phase 1 uses mass and volume of specific parts to understand overall volume and mass of the structure. Phase 2 uses mass and volume plus the forces of gravity to determine reaction forces upwards and the uniformly distributed load, UDL, as well as the dead and live load. Phase 3 then takes the UDL and the reactions to determine the bending moments and shear forces of the bridge, specifically in parts holding the weight of the traffic in the S-beams. Our aim of this phase was to analyse the bridge design using a completed bill of materials. By separating the structural members of the bridge, we were able to use engineering physics. The SI units international system of units for this phase was meters cubed for volume and kilograms for mass. The product dimensions were displayed in millimeters, so when calculating our bill of materials, we converted all our dimensions into meters. We used volumetric density and linear density to calculate mass and area times length to calculate volume, then added them together to find the total for the bridge. With an understanding of the members' volume and mass, we determined load-bearing capacities and passive active loads, internal forces, so that the structure lasts over time for its intended purpose. We rounded the significant figures to 2 as the smallest length was to 2 significant figures. For this phase and the next, we needed to understand the difference between mass, kilograms, and weight, newtons, for force. Here we use mass kilograms, and the next slide we will calculate weight.
The aim of this phase is to analyze the forces and pressures acting on the bridge. To calculate and find the live load, we used pressure times acceleration on the bridge. Our live load resulted in 100 kilonewtons. To find the dead load of the bridge, we used mass times acceleration for each member and added them together, which you can see on the next slide. By determining the dead loads, we were able to find the UDL of the S-beam by finding the total dead loads of everything on top of the S-beam itself, which gave us 52,735 newtons. We divided it by 2 to get the weight of one S-beam, and then from the UDL of one S-beam, we divided the weight by the length of the bridge, which gave us 2,109.4 newtons per meter. Using the UDL, we will determine the reaction forces from the structure, which will be explained in the next slide. Continuing phase 2 from the UDL, we multiplied by the bridge length and used the sum of mass formula to calculate the percentage of each point load girder reaction to then multiply by the UDL. Using the sum of mass formula, we solved first for R2, which we made R1 equal to 0, which was the point of rotation to be able to find R2, which resulted in 25,848.34 newtons. And for R1, we used the formula F minus R2, which resulted in 13,443.83 newtons, which we multiplied by 2, which resulted in 26,887.66 newtons. As the point load reaction is equal to the forces acting downwards in the structure, the reactions are equal and opposite. For columns, we added the weight of half the girder onto R1 or R2, depending on what column it was, and for the ground reaction, we added the weight of the columns. Each column was done separately as they both had different weights.
For the sake of phase 3, we rounded the reaction forces and UDLs so that they would align accurately by 1000 newtons per meter and the girder reactions by 10 kilonewtons, so that when using rounded answers during phase 3, all numbers are as accurate as possible. Our aim is to evaluate the internal stresses in the main S-beam of the bridge to identify the maximum and minimum points of shear stress and bending moments, as well as where there is no shear stress or bending moments. To do this, we calculated all shear stress using the first formula and bending moments along the main S-beam using the second formula. To calculate where no shear stress or bending moments existed, we looked at the graphs, and using the calculations, we could see that there were no shear stresses at the start of the beam, 1.2 meters, between 6 and 6.5 meters, 11.5 meters, or at the end of the beam. The minimum was minus 10.8 kilonewtons and maximum was 10.9 kilonewtons for shear forces. The bending moments minimum was minus 1.5 kilonewtons and the maximum was 26.6 kilonewtons. There were 4 points of zero forces at 0 meters, 12.5 meters, between 1.2 and 1.5 meters, and between 11 meters and 11.5 meters for the bending moments. We used 27 reaction points to analyze the internal forces and make the graph and calculations as accurate.
With an understanding of the forces of the bridge and where the reactions will impact its durability over time, we can see why certain materials were used and that were designed to have zero or minimal forces that break or damage the bridge. We can also plan for future repairs and minimize damage to the structure. After our analysis of the bridge design with the bill of materials, dead and live loads, UDL, point load, reaction from the girder, columns, and the ground, we can now understand and evaluate internal forces and the overall basic structural mechanics of the bridge and structure we will analyze in the future.